Hey math fans, Alex here, and today we're going to talk about independence of events. So let's go ahead and get started. So what does it mean for two events to be independent? Well, if events, we'll say A1 and A2 are independent, what that means is that the occurrence of one does not affect the probability of the other. Okay, so i.e., perhaps, event A1 doesn't influence or affect the probability of A2 occurring, okay, and vice versa, A2 also doesn't affect the probability of A1. Okay, so this might seem a little out of left field, but with the discussion on conditional probability, this is extremely easy to formulate. Okay, so with conditional probability, this is easy. This is easy to formulate into a definition. We can go ahead and just take this as a definition. So definition. So A1 and A2 are independent if and only if we have that the probability of A1 given that A2 has occurred is equal to just the probability of A1, and likewise the probability of A2 given that A1 has occurred is simply just equal to the probability of A2. Okay, so what that means is the condition that A2 has occurred does not affect this probability. It's the same probability, with or without A2 occurring. Okay, and vice versa for the other event. Okay, now, there is a more useful formulation that we can derive from this. Okay, so without loss of generality, I'm gonna go ahead and take this condition right here, and we're gonna mess around with it a little bit more. So we have that if the probability of A1 given A2 is equal to the probability of A1, that's going to go ahead and imply what? Well, the definition of conditional probability, recall, is that the probability of A1 given A2 is the same thing as the probability of their intersection, all divided by the probability of A2. Okay, and that's going to equal the probability of A1. Okay, and that's going to imply, if you multiply both sides by the probability of A2, then you get a more useful condition of independence of events, which is that two events are independent when the probability of their intersection is just the product of their probabilities. Okay, now, you'll see before I box this, because I do want to box this, that it would be the exact same argument in this case, right? Because multiplication is commutative in this case, so we do have this formula. Okay, so this is independence of events. All right, let's do some examples. All right, so example 4 says that, suppose you are picking cards from a standard deck of 52. Let the event A be picking a spade, and let event B be picking a queen. And we want to know if A and B are independent. We'll recall that the probability that events A and B are independent if the probability of their intersection is equal to the probability of A times the probability of B. So in order to find that, we have to find all the individual probabilities. Okay, so what is the probability of picking a spade? Well, a spade is one of 4 different suits. Okay, so that's going to go ahead and be 1/4. The probability of B, so we're picking a queen. Well, how many queens are there in a deck? Well, there are 4 out of 52, which is 1/13. Okay, and what's the probability of their intersection? Okay, well, the probability of their intersection is the number of ways that that can occur divided by the total number of outcomes. Okay, so how many different ways can you pick a spade that's also a queen? Well, that can only happen in one way. There is only one queen of spades, and there are 52 total cards. Okay, so all we have to do is check a little condition. Okay, and the condition that we're going to check is that the probability of the intersection equals the product of P of A and P of B. Okay, but this is clearly true. This is equal to 152, so that's true. So A and B are indeed independent. Okay, let's do another example. All right, so this example says, suppose 2 dice are thrown and let the events A be that the first die turns up odd, B be the event where the second die turns up odd, and C be the event where if you count the total number of dots, you get an odd number. So the question is, are events A, B, and C independent? Now, I didn't really formulate a definition of what it means for 3 events to be independent, but let's just kind of see where things lead. Okay, so it might benefit us to calculate some probabilities. So we note that the probability of A occurring is clearly 1/2. Right, the first die, there are 3 odd numbers and 3 even numbers, so we get 3 out of 6, or 1/2. We get that the probability of B occurring, that's also 1/2. And the probability of C occurring, well, that's actually less trivial. The total number of spots is odd, and I actually go ahead and claim that that is also 1/2. Okay, and I'm going to leave it to you as an exercise to prove that. You essentially have to enumerate all the different sums of odd numbers. Okay, so if the total number of spots is odd, well, you could get a 3, a 5, a 7, or a 9. And what you're going to have to do is you're going to have to list out all the possible ways of getting a 3. So like a 1 and a 2, or a 2 and a 1. And you have to do the same with 5, 7, and 9, and 11. And when you enumerate all of those, you should get 18. And there are 36 ways to, 36 different outcomes from rolling 2 dice. Okay, so 18 over 36 is 1/2, but make sure you kind of show that as an exercise. Okay? So, we know that A1 and A2 are clearly going to be independent, right? Because the first and the second die have nothing to do with each other. Let's go ahead and kind of do some other conditional probabilities. So what is the probability of, let's see, B, well, okay, let's do this one. Probability of C, given that A has occurred. Well, the probability of getting an odd sum, given that the first die is odd, well, if the first die is an odd number, and I want to know the probability that the total number of spots is odd, well, the only way that I'm going to get an odd number is if the second die roll is even. And that can occur in 3 of 6 ways. So this conditional probability is actually 1/2. Okay, likewise, the probability of C given B is also 1/2. Okay. And now we get that the probability of C given A was just the same as the probability of C. And by our first definition of independence, this implies that So A and C are independent. That means that A has no bearing on the probability of C whatsoever. Likewise, the probability of C given B is also 1/2, which is the same as the probability of C. So we get that C and B are independent. Okay. And, well, the probability of A given B, that's clearly the same as, well, I guess I should do B given A. Doesn't really matter, but the probability of B given that A has occurred, well, after you roll the first die, and that's odd, that has no bearing whatsoever on B turning up even or odd. Okay, so that's 1/2, which is also the probability of B. Okay, so we get that, A and B are independent. Okay, however, let me just compute the following. I want you to note that the probability of the triple intersection A intersect with B intersect with C, I want to note that that is going to be what? Well, if the first die turns up odd and the second die turns up odd, that means the sum is going to be even and never odd. So the probability that all three of these events occur is 0, but the probability of A times the probability of B times the probability of C is equal to 1/2 times 1/2 times 1/2, which is 1/8. So we get that the probability of this intersection is not equal to the probability of A times the probability of B times the probability of C. So although A and B are independent, B and C are independent, and A and C are independent, we can go ahead and say that A, B, and C are what's called pairwise independent. Okay, but it doesn't feel right to say that they are independent themselves. And I know that, again, I haven't really defined independence for 3 events, but hopefully this example motivates the following definition. Okay, so definition. Let's be more general about it now. So we're going to go and say that the events A1 all the way through AN, we can say that they are independent if we have the following chain. We have that the probability of AI intersect AJ is equal to the probability of AI times the probability of AJ. Okay, so for any I and j between 1 and n, then independence works for 2 events. Okay, but you also have to show it for 3 events, so I'll just do one more. So the probability of, AI intersect AJ intersect AK, that also has to equal the probability of AI times probability of AJ times the probability of AK. And so on and so forth. You can do this for, quadruple intersections and whatever. And finally, the probability of, we'll say A1 intersect all the way until AN, because there's only one way to, order those, because in sets it doesn't really matter. And that has to equal the product, probability of A1 times all the way up until the probability of AN. So a lot of things to check, but for 3 events, certainly you have to prove pairwise independence as well as independence with 3 events. So, by this definition, then you can go back to example 5 and go ahead and conclude that those are not independent, although they are pairwise independent. Okay, another definition. I'm trying to set us up for the Borel-Cantelli lemma, which we will prove in the next video. But another definition, okay, this time we're going to go ahead and be given an infinite sequence of events. Okay, suppose that A1 through AN, suppose that those are independent. Okay, for any n. N could be 1,000,000, and these would all still be independent. Okay, then we say that A1, A2, etc. is we say it's a sequence of independent events. Okay, basically you can think of it as like if the partial sequence A1 through AN is independent for any n, well then this infinite sequence has to also be, a sequence of independent events. Okay, now I will go ahead and state and prove the second Borel-Cantelli lemma in the next video, but one more thing that I wanted to do is I wanted to kind of state a lemma to the lemma, okay, because we're going to just use it in the next episode. So, lemma, this is really a statement about numbers. Really what it is that 1 minus x is going to be bounded above by e to the minus x for x positive. And I want you to go ahead and prove that as an exercise. Okay, so proof exercise, although I will sketch out kind of the idea. Okay, so a sketch of the proof. And this is really an exercise in calculus. I mean, I guess there are other ways of doing it, but probably calculus is your best bet. Okay, so how do you prove an inequality? Well, consider the function f of x is equal to 1 minus x minus e to the minus x. If this inequality were true, then 1 minus x minus e to the minus x would be less than or equal to 0. Okay. And essentially your goal is to use calculus, namely the first and or the second derivative test, to show that f of x is less than or equal to 0 for x non-negative. Okay, so go ahead and do that as an exercise, and we're going to use that as well as prove the second Borel-Cantelli lemma in the next video. Thank you so much for watching. Hope to see you there.